Okay, let us begin lecture number 12 of machine learning. I hope you can hear me. Can somebody say that you can hear me?
Yes, sir.
Okay.
Sir,
Yeah.
the messages on the group are saying that they did not know that it was a class today and they are busy with other stuff right now, so they will watch the video,
Yeah, that's
get
fine.
recorded.
That's fine. That's fine.
Okay, sir.
Anyway, so uh, anybody has a question? I know one of you asked the question that I should cover uh, uh, Bayesian uh, what Bayesian what classifier again. Okay. So let us look at that once more. So let us say you have a system where you have, let us say, 4 classes. Okay, you have classes. The output classes are A, B, C, and D. Okay. So what Bayes classifier? Although it is very intuitively, it is easy to understand that if you uh, find out the probability, okay, probability that your y is equal to a for a given value of x, okay, you find out these 4 probabilities, okay, y is equal to b given x is equal to x0. X0 is a specific input, okay, and probability y is equal to c given x is equal to x0, and probability y is equal to d given x is equal to x0. Okay, your output can have how many possibilities? Your y can have how many values? It can have only these 4 values, a, b, c, and d. Okay, and I am by some magical powers uh, we have done what? We have found out these 4 probabilities. Okay, what Bayesian classifier or Bayesian theorem or the best possible classifier, what mathematically it can be proven. I don't know how to prove it, but it can be done. That if you assign the output, okay, your actual y, okay, the predicted value of y, the predicted value of y is assigned to be whatever is the maximum of these. Okay, maximum of these 4 probabilities goes there, that which of I am any whichever value has the highest probability, that becomes your predicted output. Okay, if you do that, then you will get the best possible outcome. Okay, your error rate will be minimum. Okay, so that is what Bayesian classifier or the Bayesian theory is primarily is. Do you have a question now? Was it Vaishnavi or Tanya who asked this question?
So, sir, I asked a question.
Yeah. Is
But,
it
sir, isn't that what it already was? Like, what's the difference between this and the previous classifier then?
the only difference is that how do you define this probability? That is the question. It is exactly the same. Actually, that was a that's why I said that I should have covered this before covering that. But the basic concept was that if you assign the class which gives you the highest probability to the output, that gives you the minimum error. That is the basic theory. Okay, the main problem is how to find out this probability. Okay, one estimate of the probability was using that uh, कौन सा
Exponents.
logistic regression. Yeah. Okay,
Yeah.
is that all
Okay,
right?
sir. Yes, sir.
So the question is how do you हाँ चलो ओके सॉरी सो द अब बात नहीं करनी क्लास के दौरान बाद में बताना सब ठीक है so the main question is how do you find these probabilities. Okay, again that is the most difficult thing to answer. How do you find these probabilities for each of these classes? It is very difficult. Okay, so that is what we are going to try to answer using another more precise estimator, okay, compared to logistic regression, okay, which is linear discriminant analysis. Linear discriminant analysis, LDA. Okay. So let us define a few terms before we move on to where is the duster? So pi k is defined is a symbol that we give to this particular probability of finding class k. Okay. So if you have, so we have a system, okay, where we have 1, 2, k classes, okay, 1, 2, 3 capital K classes. Pi small k, this is a small k. So please try to see the difference between capital K and small k. Let me try to make it a little better. Okay. So what is the probability of finding an output which is class k? Any idea how you would do that? Let us say you have a data set. Can you find this probability? Probability of an output belonging to class k, irrespective of what the input is. Okay, nothing to do with the input at all. Okay, only that the output belongs to class k. How would you do that? Any idea? You have a data set given to you. Okay, you have a data set, inputs and outputs. Any idea how you would find this out? Or how would you estimate it? कैसे करोगे? Dipanshu? Vaishnavi, you were trying to say something. Let me ask you first.
Based on the previous outputs, we can make boundaries.
Yeah, we are going to do this estimation only from the data set that is given to you, the training data set. So how would you calculate this?
Boundaries.
Huh?
We can make boundaries for the K class.
Boundaries? What do you mean?
So
it has nothing to do with the input at all. Okay, what we are just trying to say, what is the probability of finding a class K? Dipanshu, any idea?
So like if we have labels on the data, like if we know what belongs to which class, so it's simple probability like number of that class divided by total number of data.
Yeah, that is good. So we are going to take, the ratio of k, okay, so number of times you find k divided by the total number of data points. Okay, number of times you find k, okay, you find k divided by total number of data points. Is that okay? So we have nothing to do with the input at all. Okay, we are just trying to say how many, what is the possibility that that class k will appear in the output. Okay, how do you do that? If let us say you have a data set of 100 points, okay, and you have 5 classes. Okay, you have 5 classes and you have a data set of 100 points, and your class number 10, let us say, appears for what was I trying? Yeah, 5 times. Okay, out of 100 data points. So then what is the P10 or pi 10 going to be? Okay, in this particular example, what is pi 10 going to be?
5 by 100.
5 by 100. Okay, is that all right? So we are not worried about how the input is affecting my output at all. Okay, I'm just looking at what is the probability that I'll find a particular class. Okay, that is all. Okay, is that okay? So this is also called as prior probability. Okay, it is called as prior probability. Why is it called as prior probability? We are trying to find the probability of a particular class before knowing anything about the input. Okay, is that okay? Does that make sense? Dipanshu, does it make sense to call this prior probability?
Yes, sir.
Okay, we have no idea what the input is going to be. We are just trying to see what is the possibility that a particular output is going to appear. Okay, and which are basing on trying to find the ratio of number of times that input previously appeared or divided by the total data set that I use for training. Okay, so that is one definition. The second is FKX. Okay, what is FKX? The probability that x is equal to the input is equal to x given y is equal to k. Is that okay? Do you understand what is going on over here? So this is your density function. So density function in class K. Okay, for a particular class K, how is your input distributed? Okay, is that okay or no? Does that make sense? So maybe your input is distributed Gaussian in one class. It is distributed maybe in a t sort of distribution in another class. Maybe it is a constant in another class. Do you understand what this means? That if you have decided that you're choosing a specific class K, in that specific class K, how is your x distributed? Okay, that is what FKX is. Okay, so that is and let us now apply Bayes theorem. Okay, if I apply Bayes theorem on these, what do I get? I'm going to get something like this. So what do I want to calculate? What do I want to calculate? मुझे क्या calculate करना? ये मुझे let us say somehow magically I know this. Okay, this is the density function of input for a given class K, and I obviously know this. And so what was my goal in when we were trying to apply this Bayes classifier? What was I trying to find out? I was trying to find out the probability that y belongs to a class K, okay, given that x is equal to a value x. Isn't it? That's what I was trying to find out. I still want to find that out. Okay, but what is Bayes theorem going to do? It is going to help me using these values. Okay, can you see that? Can you do a reverse calculation in one sense to find out this using these? I'll give you a couple of minutes to think about it based on what we covered in last two classes. Okay, try to come up with a formula for this.
Sir, is this the base formula?
क्या हाँ हाँ यूजिंग बेस फॉर्मूला जो हमने पहले पढ़ा हुआ है उसको लगाओ इन में
Sir, so
It will
this
be
will
pi
be
k into
पाई के इंटू
probability of x equals to x given that
या दिस वन एफ के एक्स
fkx
ओके गुड डिवाइडेड बाय
divided probability of x
probability of x which can be given by what k is equal to 1 to capital K, okay, or let me call this as j. Okay, j is equal to 1 to capital K pi j into f j x. Is that okay? ठीक है? So we are applying Bayes theorem to calculate the probability that y is equal to a class K given an input x. Okay. So this is all fine and dandy, but the question is, how do you come up with these values? Again, we have again transferred the responsibility to something else. Okay. Again, now we need to estimate the values of pi k. I have given you one way of estimating the value of pi k. Okay. So that part is easy, but calculating fkx is not that straightforward, okay? But we are going to make certain assumptions to make our life easier. One of those assumptions is what? Any idea? What is the what do we normally assume most of our distributions as? क्या करेंगे?
Independent.
Huh?
Independent.
No, independent is fine, but what is the specific distribution that we're going to choose?
Normal.
Normal distribution, correct. Okay, so we are going to estimate this density function as a normal distribution. Okay, so so we're going to call this as a normal distribution. Okay, and uh, what is the definition of normal distribution? What will it look like? So fkx is going to be 1 over root 2 pi into sigma k, ठीक है, exponential minus क्या होता है बताओ, x minus mu k whole square divided by 2 sigma square. Is that correct? सही है गलत है? Yeah, it is correct. Divided by 2 sigma k squared. Is that all right? Anybody wants to dispute this definition of normal distribution? This is how it looks like. ठीक है? So now we are going to make even more assumptions. We are going to assume that all the distributions, so we'll have k different distributions, capital K distributions for this, isn't it? With capital K values of mu and capital K different values of sigma. Okay, mu is your mean and sigma is your what is sigma? Sigma squared is your variance. Okay, so you will have capital K different values of mu and capital K different values of sigma k. Again, we are transferring the responsibility further down. Okay, how? Obviously we do not know the values of mu and sigma. What do? We make another assumption. What is the assumption that we are making? We are saying that all distributions are equally distributed in one sense. Means the variance of all the distributions is the same. Okay, so I'm going to remove this k and just call this as sigma. Okay, the variance of all the capital K distributions is exactly the same. Okay, so I have removed the subscript k from my distribution definition. Okay, and just left it as sigma. Okay, so sigma 1 is equal to sigma 2 is equal to sigma capital K is equal to sigma. Okay, that is my new definition of sigma. Okay, so we have made our life a lot easier. So now what is the goal? What is the goal over here? In Bayes classifier, what does the Bayes classifier do? क्या करता है वो? We calculate all these probabilities, and what do we assign our? So what is our end goal? Is to maximize this probability. Find the class K for which this probability is maximum. Do you all agree?
Yes.
ठीक है ना? We have to find the class K for which this probability is maximum. So maximizing either this or maximizing the log of this, would it make any difference? Can I maximize the log? Can I maximize the log? मैं इसका log ले लूँ दोनों साइड में तो कोई परेशानी है, उसको maximize कर सकता हूँ ना मैं? Is it wrong or no? Maximizing this is the same as maximizing the log. Do you all agree? हाँ या ना दीपांशु? इसका log ले लूँ कोई परेशानी है? बोलो भाई.
Yes, sir.
नहीं वैष्णवी, I'm fine with you. I'm asking Dipanshu. I think you're not convinced. Do you think if x1 is greater than x2, do you think log x1 is going to be greater than log x2?
Yes, sir.
Do you agree?
Yes, sir, it's fine. I get
It's
it.
fine, no? So now if you maximize this or you maximize the log of this in both the cases, obviously please understand that we are not trying to maximize the magnitude. Magnitude is talking about the mathematical value, the
Yes,
arithmetical
sir.
value. Okay, so the log or maximizing the log is also going to be the same. I can do
Yes,
that.
sir.
Okay.
Log is also increasing
Huh.
function. So
Okay.
yes.
One more thing, the new denominators of all the capital K different probabilities, the denominator is the exact same. Do you all agree? Denominator same है या नहीं है?
So we can just maximize the numerator.
Yeah. So since the denominator is the same, we need to just maximize the numerator. Okay. And maximizing the numerator or maximizing the log of the numerator is going to do the same thing. So our goal becomes, let me erase these. So our goal becomes to maximize what? Maximize the log of the numerator. Okay. Maximize or find the max the k for which this becomes maximum. Okay, what becomes maximum? The log of pi k into f kx. Okay, find the k for which this becomes maximum. Okay, so now you could also say, let me let me do something. Let me say that we can also say that this is equal to log pi k plus log f k x. ठीक है? We can let us leave log pi k for now. Let us look at log f k x and take log of this. Again, since 1 over root 2 pi sigma, what is that? That is the same in all of these. So do we need to worry about that? Do we need to worry about that when we're talking about log f kx? 1 over root
No,
2,
sir.
we don't have to worry about it because that is common in all the values of k. Okay, so we do not need to worry about this. The only thing that we need to worry about is this. Again, we can forget about, so log of this is going to give me minus x minus mu k squared, okay, over 2 sigma squared. Is it correct? Again, maybe we need to worry about that because that is going to play a role here. Okay, so this becomes equal to this. Okay. So now we have this quantity and अब हमें क्या करना होगा? So we have log pi k minus this. So I can do what? I can
Sir?
take, yeah.
सर वन हाँ मैं वो कह रही थी वो सेम रहेगा
Huh?
सर 2 सिग्मा स्क्वायर सेम नहीं रहेगा
No, but 2 sigma square is getting multiplied by log pi k. ठीक है ना?
ओ ओ ओके ओके
ठीक है ना? So therefore it is not that straightforward.
So we can we differentiate it?
Can we differentiate? What do you mean? I made one mistake that we could have avoided, which was to do something about this. let us leave this over here. We could have taken, नहीं वो नहीं कर सकते.
सर हमने इनिशियली एफ के एक्स एज्यूम किया है कि सब सेम डिस्ट्रीब्यूशन है ना.
नहीं सेम डिस्ट्रीब्यूशन नहीं है. म्यू के सबका अलग अलग है, सिग्मा सबका सेम है. तो width of the distribution is the same. Okay, but the means of the distributions are different. Okay, so if I were to draw two distributions, they will look something like this. Okay, one distribution may be like this. The other distribution will have the same exact width, but the means are different. Okay, so this may be mu1, this may be mu2. Okay, is that all right?
Okay, sir.
So let me say something about this. So let us see. So this is log pi k. Let me erase these. Log pi k minus x squared minus, no, minus is fine, mu k squared plus 2x mu k, okay, over 2 sigma squared over 2 sigma squared over sigma squared. Is that all right? Does that seem fine? अब x स्क्वायर को कैसे गायब करें? मुझे x स्क्वायर को गायब करना है. कोई तरीका है x स्क्वायर को गायब करने का? Can I get rid of x square any way? Yeah, we can. Oh, we can get rid of x square, thank God. Can we get rid of x square? x square को गायब कर सकते हैं इसमें से? हाँ?
डिफरेंशिएट कर देंगे तो 1 डिग्री कम हो जाएगी.
नहीं डिफरेंशिएट क्यों करेंगे? x स्क्वायर को गायब कर सकते हैं नहीं कर सकते ये बताओ. मैं कह रहा हूँ इस x स्क्वायर को कंसिडर करने की जरूरत ही नहीं है मैक्सिमाइजिंग फंक्शन में, क्योंकि हम इसको मैक्सिमाइज करने की कोशिश कर रहे हैं. वी डू नॉट इवन नीड टू वरी अबाउट दिस. व्हाई? वन ऑफ दोस थिंग्स इज दैट सिग्मा स्क्वायर इज द सेम फॉर ऑल ऑफ देम. ओके, दैट इज वन थिंग. व्हाट एल्स? व्हाट अबाउट x? x क्या है? When we are trying to maximize something, when we are trying to find this, what is the value of x? हम क्या कर रहे हैं? एक x fix कर दिया, उसके बाद हम we are trying to find the k for which the probability, this probability is going to become maximum. Okay, so what can we do about this? Vaishnavi, you said something? क्या कर सकते हैं बताओ इसका?
वो सेम रहेगा सबके
हाँ वो
लिए,
सेम रहेगा सबके लिए.
जैसे-
So we do not need to worry about this. Okay, it is going to be the same for every. So please understand that. What is the procedure that we are following? We have fixed the value of x. Okay, we are given an input x, and we are trying to find the different probabilities for which for that given x y is equal to k is maximum. Okay, well, the probability for which then the y is equal to k is the place where the probability is maximum for any specific value of y. Okay, so since for this particular maximization, this is what? This is a constant. ठीक है ना? ये हर किसी k में अपेयर करेगा with the exact same value. Do you all agree? अगर मैं k की वैल्यू 1 रख दूं, 2 रख दूं, 10 रख दूं, उन सब में ये वैल्यू क्या रहेगी? सेम रहेगी ना दीपांशु?
यस सर.
ठीक है ना? So we do not need to worry about this. So but we need to worry about this. इसको नहीं नेगलेक्ट कर सकते. क्यों नहीं नेगलेक्ट कर सकते हम इसको?
म्यू के करना होगा.
म्यू के है उसमें. म्यू के takes different values. Okay, based on what your specific distribution, where the mean of the distribution lies. Okay, so therefore we need to worry about this, but not this one. Okay, pi k obviously has different values. Okay, depending on the value of k. Okay, we will have different values of pi k. So what we are looking for? You are looking for the dependence on k. Okay, if something is dependent on k, you cannot neglect that. If something is independent of k, then you can neglect that. This is independent of k, you can neglect that. This is dependent on k, you leave here. This is dependent on k, you leave here. This is dependent on k, you leave it here. Okay, everything else is gone. Okay, so now you're trying to maximize this particular function. Okay, instead of maximizing whatever we were talking about here, we are trying to maximize this function. So this particular function let me write it again, is called as the delta k. Okay, x, okay, is equal to log pi k minus mu k squared over 2 sigma squared plus x mu k over sigma squared. Okay. So this becomes your, so this is called as the discriminant function. Okay. We have already talked about discriminant functions, but in a sort of an informal way. So this is your discriminant function. We have talked about it, which in the form of what? Yeah, decision boundary. Okay, so decision boundary was one discriminant function. Okay, similarly you have a discriminant function over here, and the reason we call it this, as I just erased this, but I just wrote the name previously. I wrote the name of this particular methodology. It is called as linear discriminant analysis. Okay, so because this function is linear in what? X. Okay, this discriminant function is linear in x, therefore we call this as linear discriminant analysis. Okay, linear in x, in x. So again, we have come up with all this, but we have still not answered the question, how will you come up with the value of mu k and sigma squared? ठीक है, हमने बहुत सारे we have made millions of approximations till now, but we have still not found out the value of mu k and sigma squared. How will you do that? कैसे करोगे? क्या करोगे भाई? कोई तरीका है to find out the value of mu k and sigma squared?
जो डेटा सेट हमें दिया हुआ है,
हाँ, उसी से approximate करेंगे. So LDA helps us in approximating these values. Okay, so LDA helps us in approximating these values. I'll go to that in a moment. So yeah, let me do that. Okay, so where am I? I'll erase these. So LDA helps estimate sigma and mu k. Okay, and those estimates, we in most of the statistics we usually so the true value is called as sigma. Okay, and whenever we are estimating the true value, we put a hat on top of it. So the hat stands for estimate. Okay, we obviously do not know the true value of sigma, so we can only estimate. Okay, so that sigma hat is given by 1 over n minus k. This is capital K. Sigma small k is equal to 1 to capital K sigma I such that yi is equal to small k is x I minus mu k, estimate of mu k squared. Okay, that is sigma squared. Okay, this is the estimate of sigma squared, and the estimate of mu k is given by 1 over nk sigma I such that yi is equal to small k xi. Can you see what this is? What mu k hat is? I know sigma is a little more involved, but let us look at mu k hat. Can you visualize what that is?
average in that kth
Yeah,
class.
kth class. The average of the inputs in the kth class is your mu k. So nk is the number of points in the kth class. Okay, number of observations in the kth class. Xi, this is the sigma of the sum of all the values for which the output is equal to small k. Okay, and we are taking the average of that by dividing by the total number of those observations. Okay, so this is the average of the k values. Okay, the input corresponding to the k values, and sigma squared again. I don't know how to just show that, but I think it is, if you know what the definition of variance is, probably you can figure that out. Okay, let's not worry about that. So let us do a small example. So what is your discriminant function going to be? Again, pi k has already been defined. What is pi k? The approximation of pi k is going to be, it is going to be nk over n. Is that all right? Nk is the total number of observations in the kth class divided by the total number of observations. Okay, so nk divided by n is going to be your pi k hat. Okay, approximation of pi k. And finally, we can replace, so this was the true discriminant function using Bayes theory. By applying the LDA approximation, linear discriminant analysis approximation, and you're doing all this, this becomes, you put a hat over here. Obviously, this will be a hat, 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 and this will be a hat. Okay. So now let us do one example, and then we'll stop for today.
Excuse me, sir.
Yeah.
Sir, in that sigma function, estimate sigma function,
Yeah.
total is it an average kind of, because the total entries will be n, but we are doing 1 upon n minus k.
I know the students always ask the questions to the questions to which the teacher does not know the answers to. I I know that this is the true definition of variance, but I do not know where this n minus k comes from. So let me look at that, and I'll get back to you in the next class. Okay.
Okay, sir.
But even if you define variance, if you don't worry about all this, generally when you define variance, usually you have something like this. Okay, I don't know what is the origin of that, but let me look into that, and I'll get back to you if I can come up with a reasonable answer which can be explained to you guys. Okay.
Okay, sir.
Where am I? Where am I? Yeah, I was trying to give an example. Yeah. So let us say we have uh, capital K is equal to 2. Okay, there are two classes, and I am assuming that both of them are equally divided. Okay, so the if you look at your training data, the number of times class 0 appears is the same as the number of times class 1 appears. Okay, both of them are the same, or 1 or 2, whatever you want to call it over here. So I'm saying that pi 1 is equal to pi 2. Okay, class 1 appears the same number of times as the class 2, or the probability of finding class 1, the prior probability of finding class 1 is equal to the prior probability of finding class 2. Okay, so now can you do a calculation for that? Now if you were to apply this discriminant function, what will you get? क्या होगा? क्या होगा हमारे discriminant
Phi 1
function का?
and phi 2 will be 0.5.
हाँ? So
Phi 1
delta
and phi 2 will be 0.5.
delta 1x is going to be, we do not need to worry about this anymore because both the pi's are the same. So I can forget about this from my discriminant function. The only thing that I have to worry about is these two. Okay, so it comes out to be mu1 x minus over 2 sigma squared minus,
So denominator is also same.
yeah, sorry, in this case, yeah, denominator is also the same, so we don't need to worry about the denominator also. Okay, so this becomes,
We will have to multiply by 2. Yeah. 2 mu 2x minus mu 2 square.
Sir, you are not audible. Hello?
Sir,
Sir, you are not
you're not
audible.
audible.
Hello, can you hear me now?
Yes, sir.
Yeah, batteries from my microphone were gone. Anyway, so uh, where will the decision boundary lie? क्या होगा decision boundary का? Any idea what the decision bound or what does the data look like? In this case, we have how many variables? How many input variables do we have? कितने हैं? हमारा जो original data है, अगर if you were to look at your data set, your output is y and input is how many inputs do you have?
Two kinds of input we have.
We have one input x, isn't it? One dimensional input है या नहीं है?
Yes, sir.
ठीक है ना, तो हमारा डेटा अगर हम प्लॉट करेंगे तो क्या लगेगा, एक लाइन लगेगा पूरा डेटा. सो वे योर डिसीजन बाउंड्री किस टाइप की लगेगी तुम्हें? डिसीजन बाउंड्री कैसी होगी अगर अगर लीनियर डेटा है, मतलब इफ योर डेटा इज सिंगल डायमेंशन. हाँ,
A single
Point.
सिंगल पॉइंट.
point.
ओके, सो कैन यू फिगर आउट वेयर योर डिसीजन बाउंड्री विल लाई? हम कैसे डिसाइड कर रहे हैं? हाउ आर वी मेकिंग अ डिसीजन? वी आर सेइंग दैट your estimate, your output estimate y is equal to 1 if what? हम क्या कह रहे हैं? Y is equal to 1 if delta 1x is greater than delta 2x. हाँ या ना? कह रहे हैं हम या नहीं? Am I saying that or no? Come on.
Yes, sir.
ऐसे तो डिसाइड कर रहे हैं हम कि कौन सी क्लास में जाएगा. If delta 1 is greater than delta 2, I am saying that I belong to class 1. Okay, and otherwise is equal to 2 if the opposite happens, delta 2x is greater than delta 1x. Okay, so where is your decision boundary going to lie?
When delta 1x is equal to delta 2x.
Yeah, so delta 1x, so decision boundary is where delta 1x is equal to delta 2x. Okay, so what does that come out to be in this particular case? इस केस में क्या आ रही है हमारी डिसीजन बाउंड्री? कैलकुलेट करो भाई. At what value of x? Huh?
Minus mu 1 square minus mu 2 square
Yeah.
divided by 2 mu 1 minus mu 2 mu 2.
Okay, that is good. But can you do some cancellations? So if you do this,
Yeah, it is mu 1 plus mu 2.
yeah, by
by
2. Okay, so if you do, if you equate these two, let me erase the remaining because we no longer need those. If you equate these two equations, you get 2 mu 1x minus mu 1 squared is equal to 2 mu 2x minus mu 2 squared. So 2
Sir?
mu 1 minus, yeah.
सर इस केस में mu1 और mu2 सेम नहीं होगा?
नहीं, क्यों होगा सेम? फिर तो कुछ बचा ही नहीं अगर mu1 mu2 सेम हो जाए तो.
Because sir, the number of times x is there when y is coming as 1 is equal to the number of times x is there when y is coming as 2. So
But that has nothing to do with x. Please understand that. The only thing is that in the output, half the times you're getting a 1 and half the times you're getting a 2. That has nothing to do with x.
अच्छा अच्छा okay okay
ठीक है
yes
ना?
sir yes
Prior, that is
हाँ
prior probability. Please understand that prior probability has nothing to do with the input. We are only looking at the output.
yes
Okay?
yes sir okay
So this comes out to be mu1 squared minus mu2 squared. Okay, what is mu1 squared minus mu2 squared? It is mu1 minus mu2 into mu1 plus mu2, mu1 minus mu2, mu gone, and finally you get x is equal to mu1 plus mu2 divided by 2. So that is your decision boundary. Okay, so if x is less than that, then you're going to assign it a 1, and if x is greater than that, then you're going to assign it as a 2. Okay, is that all right? I think we're done for today. If anybody has a question, I'll answer that. Otherwise, we'll stop. And I just wanted to remind you that you have an assignment due on this Sunday midnight. Okay.
सर एक डाउट है छोटा सा.
हाँ बोलो बेटा.
सर अगर ये मतलब हम ग्राफिकली इसको देखें तो ये जो डिसीजन बाउंड्री है mu1 प्लस mu2 डिवाइड बाय 2 ये तभी पॉसिबल है ना जब दोनों प्रोबेबिलिटी फंक्शन जो है हमारे बिल्कुल जस्ट कंटिग्यूअस हो, मतलब एक्स एक्सिस में एक प्रोबेबिलिटी फंक्शन देन तुरंत बाद उसका सेकंड क्लास का भी प्रोबेबिलिटी फंक्शन स्टार्ट हो रहा हो.
क्यों ऐसा क्यों होगा?
सर बिकॉज mu1 प्लस mu2 डिवाइड बाय 2 कर रहे हैं हम, तो उन दोनों प्रोबेबिलिटी फंक्शन के बीच का हम एक मतलब एक्सिस पे देखें तो अगर हम
हाँ
बीच में डिसीजन बाउंड्री रहेगी, और अगर हम दोनों में गैप है दो प्रोबेबिलिटी फंक्शंस में, तो बीच में जो एक्स होंगे वो हमारे इनपुट में नहीं है, इसका मतलब वो किसी प्रोबेबिलिटी डेंसिटी में लाई नहीं करेंगे.
हाँ, बट इन दिस पर्टिकुलर केस व्हेन यू आर अज्यूमिंग नॉर्मल फंक्शंस तो इनफाइनाइटली चलते जाते हैं ना. हाँ या ना?
यस सर, बट सर वो जो उनकी लास्ट मतलब वो तो इम्पोर्टेंस नहीं होगी ना, मतलब
मतलब नॉन एग्जिस्टेंट तो नहीं है ना. तुम्हारी वैल्यू तो जब आएगी जब नॉन एग्जिस्टेंट हो वो.
हाँ यस सर, दैट्स आल्सो ट्रू.
ठीक है ना? Obviously, please understand that when we are so let us say we are talking about two normal distributions, our confidence obviously becomes much smaller. Means we may define a decision boundary using this particular logic, but if our distribution looks something like this, okay, one distribution is over here, okay, and the other distribution is here. ठीक है, यहाँ पर you are right that it is negligible. Okay, so obviously we are going to our probability using this whole thing, our decision boundary will come somewhere here. But please understand that since the probabilities are so small in these regions, our confidence level is also very small regarding whether this belongs to class 1 or class 2. Okay.
Yes sir.
So if you look at obviously the probability here on this side, the probability p1 or delta 1 is going to be greater than delta 2 in this particular. Let us say this is mu1 and this is mu2. Okay, if delta 1 is obviously going to be greater than delta 2 in this particular scenario, but the delta 1 is very small, delta 2 is also very small, so means obviously we are making a decision, but it's not really a very confident decision. Okay, because the probabilities are of both these quantities is very small. Okay.
Yes sir.
So here the region of confusion, okay, the region of confusion is much bigger, okay, in this particular kind of distribution. ठीक है?
Okay sir.
Okay. Any other questions? Nope. Okay then, I'll see you on Monday, and we'll have a discussion on assignment on Monday after the class at 4 o'clock. Okay. Thank you. And please, I'll email everybody with the link for the class. Okay. Anyway, thank you. Bye bye.